Hi, today we're going to take a look at arc length. Now from geometry, we learn how to find length of lines, line segments using the distance formula. We're going to talk about that in just a few moments. Today we're going to do the same thing but for an arc. In other words, we want to find the length of the arc of this function. Let's call this function f of x on the interval from a to b. So if I draw points up here and I connect them, I'm going to go along the curve. I want to find the length of this arc, which we'll call s. To find the length of this, we will use the distance formula, and we're going to take a look at how this applies to us in calculus in just a few moments. So the distance formula we know is x, the difference in your x values squared, plus the difference in your y values squared, and we take the square root of that. Now, in order to use this for an arc, because remember, this is only for straight lines, in order for something with an arc on it, we have to set up a rule. The function must be differentiable. In other words, it must be smooth. Smooth as a baby's bottom, or smooth as a good pickup line. So the function has to be differentiable. Now, if the function is differentiable, what we're going to do is we're going to take our arc and we're going to break it into little tiny segments, like so. Little tiny segments of it. Now, the smaller the segments, the more linear it becomes. And that's very easy to see if we if we graph a function. So for example, let's say we graph the function y equals x squared. Hit enter. If I zoom in, number 4, and I think it's 3, if I zoom in on the function enough times, let's take a look at what happens. If I keep zooming in, if you notice, it looks like it's getting straighter and straighter and straighter. Well, the function's still curved, it's just that we're zooming in so much that we can barely see the curve, so it looks straight. And that's kind of what we're doing here. We're going to break it up into little straight segments, and those straight segments are eventually going to give us our curve. But for now, let's just take a look at one of these segments. We will call, if we look at this little segment right here as a right triangle, this distance right here is the difference in my x values, which is just delta x. Over here we have the change in our height, our y values, which is just delta y. Well, if you look at your distance formula, we have change in my x values and change in my y values. So what we're going to rewrite is our distance formula in terms of the deltas. In other words, instead of x1 minus x2 squared, I could write that as delta x squared. Instead of y1 minus y2, I can write this as delta y squared. And there we have it. Now, so that's going to give me the length of just a little tiny line segment, a little tiny segment right here. So we got to get all of them. Now we're going to do a little kind of an algebra trick. There's a rule in mathematics. We can do whatever we want to a function so long as we undo it. And we use that all the time, like when we complete the square. For example, if I have x squared plus 4x, if I want to complete the square, we would take half of the 4, which is 2, and square it and add 4. But the rule was if I added 4, I also have to subtract 4. We're going to kind of use the same concept here. I'm going to divide delta y by delta x. And that's going to change this to d equals delta x squared plus delta y over delta x squared. But because I'm dividing it now by delta x squared, I also have to multiply it by delta x squared. And if you notice, those will cancel, and I haven't changed the value of my equation. Now the reason we do that, take a look. I have two terms, they both have a delta x squared. I can factor that out. And that's going to give me 1 plus delta y over delta x squared times delta x squared. And now if you notice, take a look here, I can take the delta x squared out of my square root. So we get the distance equals the square root of 1 plus delta y over delta x squared times delta x. And what this does, this gives me the length of my one segment. This is the length of one segment. Now, I want to get the length of all the segments. So to get the length, I'm going to take a summation of this. 1 plus delta y over delta x squared delta x. And what we're going to do, if we do like little sub i's on those, we're going to let I go from 1 to n. And this is going to give me the sum of all of them. Well, using a bit of calculus, what we're going to do is we're going to let delta x go to 0. So we take the limit as delta x goes to 0 of our summation. This should look a little familiar to you. This is the definition of a derivative. This is a derivative. In other words, what happens is, as delta x goes to 0, delta x becomes dx. So I can now write this as 1 plus, we'll talk about this in a second, dx. Because it's a derivative, take a look. I have delta y over delta x. That's the slope. Well, we're already talking about derivatives now, so that just becomes f prime of x. And this is going to give me and because I'm taking the limit that goes to infinity, I'm going to get an integral. So I take the antiderivative from a to b, and that's going to give us our arc length. Oh, why did that go out of focus there? And so that gives us our arc length down here. And therefore we get our arc length formula. To find the arc length, we call S is from a to b of the square root of 1 plus f prime of x, the derivative of the function squared, dx. And we can kind of see how we derive it from our distance formula. So if you go to part 2, I'm going to take a look at some examples on how we can apply this. Okay, I'll see you there. Bye-bye.